don't know me, I was a student with Yvan starting 1999 as an undergraduate student here at the University of Montreal. I did the research project with him and Robert Langlands, and then I did my master's with Yvan, and then I'm now and then I did my PhD in the US. And so I kind of branched out from what I used to do with Yvan. So what I'm going to talk about, maybe I should just move this. It's annoying. All right. So what I'm doing now is related to number theory, but from a stat mech perspective, so mathematical physics perspective. So that's what I want to present today, and hopefully I'll keep it light. And I'm just going to tease you here and there with some number theory. All right. So just a little slide about information about, where I come from and what I learned from Yvan. So as I said, I started 1999 working with Yvan doing numerical simulation for crossing probabilities on the Ising model. And I got hooked, and I started doing my master's with him. My master's was on the Ising model, or Potts model more generally, on the torus. Instead of crossing probabilities, we were looking at the clusters. These were fortune cast line clusters. The first problem was actually doing the spin clusters, but that was too hard. But we could do the fortune cast line clusters, how they wrap around the torus, and you have different homology classes. So that was, and there was some nice CFT calculation in it. And similarly, around the same time, the SLE revolution started. So the Schramm-Loebner evolution, stochastic Loebner evolution first, but now it's in probability, it's referred to as Schramm-Loebner evolution for good reasons. And that was around 2001, right? And some calculation that we could do in CFT, they could reproduce using probabilistic technique. And so Yvan actually gave me the advice to do a PhD in probability with Michael Eisenman, who obviously was one of the first to propose conformal invariance. I have some slides on that. But when I got to Princeton, Eisenman was like, no, SLE is done, so I'm doing spin glasses. So I switched to spin glasses. Anyway, so I'm going to mention really some basic notions of statistical mechanics learned from Yvan. And also one thing I learned is, the usefulness of numerics when you're doing pure math. And that's going to be some of that at the end. Okay. So feel free to ask any questions. So I could have done a talk just on this paper, but this is not what I'm doing for research. So, but I wanted to put a slide on this, and I actually did that last night, and I read not the whole paper, but I reread. So this is, it's hard to actually overstate how important that paper was. That's in the bulletin of the AMS. What year? 1994. Just to give you an example, when I was in 2004 at the ICMP, the International Congress of Mathematical Physics, so Schramm actually gave a plenary lecture about conformal invariance and SLE, and he quoted that paper as the reason why I started working on this. Okay, because Schramm, was a topologist. So he started working on conformal invariance and percolation and other stat mech models in 2D because of that. And that paper quotes Michael Eisenman as the reason, one of the reasons why crossing probabilities, one of the motivation for the hypothesis of conformal invariance of crossing probabilities. I remember Michael actually told me that one day, Robert Langlands called him on the phone, and it was like, oh, Robert Langlands, the famous Robert Langlands from the IAS. And, he mentioned that conversation. So, all right, so there's some very nice sentences in that paper I just wanted to share with you. So there's this one. So there's two hypotheses, right, that they're working on that paper, universality and conformal invariance. the hypothesis of universality essentially is, crossing probabilities shouldn't matter when you change lattice. And there's this nice sentence: those experienced readers feel that this hypothesis is generally accepted and not worth examining numerically might ask themselves how much they are willing to stake on its validity in 3 dimensions: life, family, or career. Did you write that? Which one do you bet on? So anyway, but it's interesting because the state of, in terms of mathematics, what is proved, for percolation, conformally variance is proved, but only, for the triangle lattice. And so it's still a big problem to actually show universality for the crossing probability and conformal invariance. And so it's kind of stuck from the probability perspective, to be honest. So the sentence is actually says the opposite. It says, since proof of conformal invariance will likely have to wait upon proofs of universality for percolation, blah blah blah. So, with in all likelihood be slow in coming. And interestingly, historically, the conformal invariance came, for the triangle lattice, but by Smirnov, and we're still waiting for proof of universality. So that's what I wanted to say about that paper. Okay, now just on a personal level, so those are the 3 papers, so 2 papers I wrote with Yvan, also at Saint-Aubin back then, on the Ising model. So when I started working with Yvan, it was focusing on the Ising model and not really percolation at that point. And so that's my master's thesis for the Ising model on the torus. And then we looked at, again, 2D critical Ising model, some non-unitary observables. So those were CF2 papers. All right, so now I'm going to kind of switch gear and talk about number theory. So, but let's have a little transition. Okay, so very simple transition. What is the Ising model? And I'm just going to use this as a point of comparison with what I'm going to do with the zeta function. All right, so this is the Hamiltonian of the Ising model that could be in any dimension. So spin interaction, magnetic field. And then you have the partition function, right? So you have the state space, the spins, you have n spins, and you have the partition function when you sum the Hamiltonian. So interesting in probability, we don't put a minus, but I made an effort to put a minus. There's a lot of physicists in the audience. And then you have the free energy per particle, which is the log of the partition function normalized by the number of spin. And again, we never put the -1 over beta, but when in Rome. So there you go. So that's the basic terminology in statistical mechanics. Now, some important results. So you have the phase transition, first order phase transition. If the inverse temperature is large enough, that's the magnet. If you have a magnet, so you have spontaneous magnetization, and then you have Onsager solution when you have well, it works also when beta is not equal to 0, but you have an explicit solution. So Paul's argument doesn't really compute the partition function of the free energy, but the Onsager solution does that for you, and then you can explicitly look at the free energy as a function of beta and look at the analyticity properties. All right, so this is just a framework, basic framework of statistical mechanics. And I should say this is in 2D, obviously. 3D, there's an interesting result from probability, actually, by Hugo, Dominicop, and Eisenman. Peirce's argument works in dimension. Let's switch gear to number theory. So that's a change from the rest of the conference. So I'm going to look at the zeta function, and essentially, just as a punchline, I want to look at the zeta function as essentially exponential of the Hamiltonian. So I'll tell you why. So that's the zeta function when you are real part of S is bigger than 1. You sum over the integers, 1 over ns. And because you can decompose n as to prime factors, you can write this as an Euler product over prime 1 minus p to the minus s, right? You generate every integer. And that's going to be the only algebra in the rest of the talk, right? So you can decompose n into primes. All right, so over here I have a factor missing. There should be a chi-s. So this is where you know the function. Then you have a functional equation. There should be a factor here that relates what happens here to what happens there. Okay, and then you have this critical strip. So you can show that you can analytically continue functional equation in the region real part of S between 0 and 1. Now the critical line is the real part of S equals to 1/2. Now this factor is 0 at negative at even integers. But what happens is you have trivial zeros here and you have no zeros there. That's not hard to see. And then all the zeros are in that strip. And then the Riemann hypothesis tells you that all zeros are on the line. Now the question I'm interested in is not about the zeros, but rather how large, so the large values. Okay, so that's a graph of the zeta function, but it's actually log of zeta. Okay, so the zeros are sent to minus infinity. Those are this, the first zeros around. And so you have those, so you have those zeros. And then what we're interested in is actually the large value. So how this grows, okay, as you go on the critical line, as you go up on the critical line. So everything is on the critical line now. Real part is 1/2. Now the Lindelof hypothesis tells you that the log of the zeta function grows slower than log t. All right. So if you have a good eye, it's like, okay, looks like it. All right. But then you can actually state the Lindelof hypothesis. It's an equivalent statement, and that's relevant to us right now. Is I'm going to look at this as a partition function. So what I'm going to do is I'm going to integrate on some interval, some large interval of the critical line. And I'm going to integrate zeta to the power beta. All right. So number theorists call this the moments of the zeta function for good reason, right? But let's think of it as a partition function. Okay. So it's a partition function. And what's my state space? It's just all the points in my interval. And what's the energy? Well, it's exponential. So here I have exponential of minus log of zeta times minus beta. So minus logs of zeta should be my Hamiltonian. All right. And so now the question is, and the Lindelof hypothesis tells you that the partition function actually grows slower. Well, it grows like slower than any power of t as you go up the axis. Now the constant here, the implicit constant might depend on beta, but that growth is uniform in beta, if you wish, okay? That's extremely hard, okay? That's extremely hard.
Is the equal sign smaller or equal?
Where?
The last equal sign, this one.
Yeah, that's what I mean, yeah. It's not, it's smaller or equal, yeah. Actually, so the real, okay, so here's what the real growth should be. Should be like log t to some power. Okay. Now you see, that's called the moments conjecture, and it's extremely precise. So it actually tells you the part exactly, well, asymptotically the main term of the partition function. All right. And so the free energy is about the log of the partition function, right? So it should be like beta squared over 4. The free energy essentially per particle. So this is about the exponent, the free energy, but the conjecture is about, the asymptotics of the partition function itself. And so that's an interesting connection with math physics, not really the one that I'm working on at the moment, but it's a tough one. That this constant is explicit. So there's two factors, an arithmetic one, that's the A. And that's essentially a function of the primes, and you can compute that. I mean, it's explicit, okay? It's not the misunderstood one. The misunderstood one is this f beta, and this f beta is exactly the moments of the characteristic polynomial of a random unitary matrix. Okay, so if you look at this, this is very similar to how I wrote the moments of zeta, right? Except that what plays the role of zeta is the characteristic polynomial, power beta, and so the characteristic polynomial should grow like n beta squared to the 4. So that's similar to that. So that's, if you wish, the same constant you would get if you think of zeta, if you think of the characteristic polynomial as a model of zeta. And this connection between random matrix goes beyond the characteristic polynomial. So that's the curve. Obviously, the characteristic polynomial here, I'm on the unit circle. The eigenvalues are on the unit circle. So if you wish, for random unitary matrix, you know that the Riemann hypothesis is true because all the zeros are on the unit circle, and the unit circle plays the role of the critical line. All right. But of course, this is a compact, right? It's a compact interval. And so this is like essentially looking at zeta in a small interval. And so this connection, so you have this connection with the moments, but you also have connection with the zeros. There's a famous Montgomery conjecture that tells you that the spacing between zeros of the Riemann zeta function should have the same statistics as the gaps between the eigenvalues. So this is really.
Could I just ask? The right-hand side is a random variable, and the left-hand side is a number.
Random.
Oh yeah, thank you. There's an integration on the U. So the good thing about doing this on Zoom is that I can do that live. Thank you so much. Yeah. All right.
And that's with respect to the Gaussian or
yeah, it's uniform on it's the integration on the group.
So with the Gaussian measure. Oh, sorry, it's unitary. Okay.
It's unitary. Yeah. So I have a uniform measure on the unitary group. It's a compact group. Integration over the R measure. Is that clear?
Yeah.
So the moment conjecture is true. Well, we know it's true for beta equals 2 and 4. It's open for all the other beta. It's an extremely hard problem. But on the Riemann hypothesis, you can actually show that the exponent is correct. So that's a hard problem. So I'm going to go to a problem we can solve. Now, what I did is simply invert that picture I had of log zeta. So it's minus log zeta, which should be like our Hamiltonian, if I think of the moments as the partition function. And if you look at this, this looks like an energy landscape or some potential of some physical system. So this is the axis is, if you want, my state space. And, I have potential for an energy for every state, okay? And then we can ask question, the obvious question, what is the ground state energy, for example, right? Which is the same question that the large values I was referring to, except now it's the reverse, right? Ground state is minus, and large values are maximum. Okay, so what are we gonna do? So what I'm doing here, which I haven't explained yet, but I'm explaining now. So I'm going to fix an interval. So I'm on the critical line, and I'm going to pick a point on that critical line, and I'm going to look around that point. Okay. So here I say I pick a point. I'm somewhere around 10,000. I look, in an interval around that point. So that's what we're going to do. All right. So that was the idea of Fedorov and Keating, 2012. It's like, this too hard to solve the Lindelof hypothesis. So what we're going to do is we're going to pick a point that's my tau, on that huge interval, and then I'm going to look around that point. Okay. Now this is a random variable because it depends on tau. Okay. So I'm picking, if you want, a landscape on my critical line, and I'm going to look locally around it. Okay. Now I write the moment, so it's a moment in a short interval. I can write it, as I said before, as essentially a partition function, right? So exponential of minus beta ht, where now my Hamiltonian, as I said, my energy is minus log zeta 1/2 plus it. And what plays the role of the state space is all these little t's in the interval around my point of reference, okay? So essentially, we're picking a typical interval, and we're asking, well, how big is zeta in the typical interval? Okay. Now, this is a random variable, as I said. This is a random Hamiltonian because it depends on tau. Now, essentially the idea of Fyodorov-Keating is to say that this random Hamiltonian should behave like a log correlated system. Okay, so if I look at the covariance, the correlation between the value at 2 points of zeta, or log zeta, all right? Now the integral's on tau here, the expectation's on tau. So typically, what is the correlation between two values of zeta? It should be log correlated. So it decreases logarithmically with this with the distance between the points. Okay. Now here's a theorem. So we can actually compute, if you want, the free energy per particle for that partition function. So for the moments in short interval. So if I take the log of this moment in short interval, turns out that the right normalization is log t, and it's 1 over beta. You have a dichotomy, right? So here I grow like beta, and this is essentially like a constant if I look at beta at large, okay? And so there's a critical temperature, inverse temperature at 2, okay? And this is typical, okay, of a phase transition for 1 RSB spin glasses, okay? So if you know what that is, great. If not, see me at lunch, okay?
So
yes.
You wrote your thesis on that.
Yeah. Okay. Yeah. So what is the and so you have the phase transition, okay? And every time you have a phase transition, you should have what is the order parameter. It turns out for spin glass, the right order parameter is Edwards-Anderson order parameter, if you wish. And essentially what you want is compare. So you don't have necessarily a value assigned to one state, but you compare states, okay? And so what you're looking at is, okay, I take two states, so the values at t and t prime, and you can actually look at the correlation coefficient. So it's essentially, you know, the normalized version of that. Okay, so you just normalize by the variance. Okay, so it's a correlation coefficient. So between -1 and 1, it tells you how far apart those t's are. Okay. Now, if beta is large enough, what happens is the only possible correlation for coefficients are 0 or 1. Okay. So that means that either the values are really close to each other, so the large values are really close to each other, or they're really far apart. Okay. Or at high temperature, then you just get 0. Okay, so that's actually a 1 RSB spin glass phase transition. Okay. How much time do I have? Like minus?
No,
I don't know
we
what.
started a little late, so at least a big finish.
Everybody.
5, 10.
Okay, open-ended. All right, so okay, but I think I can wrap it up in 5 minutes. Okay, so that's, you know, about, if you want, the free energy, but you can also, if I drive beta to infinity, obviously the free energy per particle gives you information about the ground state. Okay, ground state energy per particle. So when you drive beta to infinity, you should get 1, okay? That tells you that the typical value of log zeta is log t in a typical interval, finite interval.
Sorry, could I just quickly ask? Could I just quickly ask? You're not looking at correlations between the zeros, right? You're looking at correlations in these ground state energies. So
Correct.
does that have anything to do with the correlations between the zeros?
Yes, yes. If you, instead of looking here, I'm looking at the absolute value, right? So the log of the absolute value, which is the real part of the log, but you can ask the same question about the imaginary part of the log, and that's about the zeros. So you have the same type of conjecture.
Okay, so this is not the usual connection between random matrices and zeros of the zeta function.
No, it's not. But I'm going to go back there soon. But you're absolutely right. All right. So now the Fyodorov-Keating, they actually have an exact, almost exact prediction for what if you want the ground state energy would be. So I'm looking at the maximum in my typical interval. Okay, so if you want the ground state, you have to do the minus, and then it's very, very precise. So it goes like log t to double log t to a 3/4. That 3/4 is important. And then after that, you have fluctuation of order 1. So remember, it is the random variable because I picked that point randomly. Okay, so those fluctuations of order 1, depending on how. And we were able to actually prove that up to this fluctuation of order 1. And then you can ask the same question. So this is about the ground state. You can compute the partition function very precisely with a correction. Okay. So now, I'm not in the free energy. I'm looking at the partition function. So it's more precise. And you can do it up to order 1. But this order 1 is stochastic. Okay. So if you want, what that means is stochastically bounded by a constant. Okay. So we can prove these things. So that was for an interval which is very short. Okay, so like interval is essentially order 1. Now, what if I take my interval and I try to make it bigger? If I try to make it bigger, the only thing we can do is intervals which are power of log t size. Okay, the interval grows like log t. What you would like to do really is interval of size t. Okay, because that interval is in the realm of the Lindelof hypothesis, but that's extremely hard. So we can do essentially log t. And then you have also these ground state energy very precisely up to order 1, okay, with different exponents. That's interesting, and we can compute the partition function. All right, to go back to the question, all right, so that's my last slide, the numerics. So there's this order 1, okay? So do you see random matrix appearing when you're looking at the large values of the absolute value? So obviously, if you look at the zeros, they should appear there, as I said, the Montgomery conjecture. But what about large value of the modulus? And that's, following the philosophy of Yvan that, you should actually get some numerics, convince yourself. That's what I did with 2 undergraduate in my postdoc. So we actually looked at, what you're looking at is the maximum of log zeta in an interval of size log t to the theta. So theta, the x-axis here is theta. And what happens is, okay, so in red is the average. So at every theta, we have some points. I don't know, like 500, maybe 1,000 points. Okay. And then this is the prediction from Fyodorov-Keating is the orange line, but you see some discrepancy. All right. And it turns out that if you want actually the right, okay, that's the blue line. If you want the right order of magnitude for this maximum, you actually have to introduce random matrix correction. And these random matrix correction arises in this order 1. And essentially is the same C beta that I gave you at the beginning that appears in the moment, okay, in the moment's conjecture. Okay, so you see random matrix influence also in, the large values in short intervals, okay? And that's, so you might, the reason why I did the numerics is because some of you might have laughed, when we actually look at t's of the order of log t, okay? Because numerically, you can do t around 10 to the 20, okay? So it's hard to capture the log t influence when you're working with 10 to the 20. And so when I presented these things, a lot of people were laughing. You will never see it. But the thing is, you can see it because the predictions are so precise. Even though log t is of the same order as log t for 10 to the 20, and essentially of order 1. So order 1, log t, log t, essentially of the same order, but they're so precise, the prediction, that if you put the 3 together, you can get pretty good numerics. Okay, there's still some discrepancy here, but I think we can explain. So the numerics were very, important to justify all these theoretical predictions that look a bit silly, log t.
What's the green stuff?
The green stuff are the points so for every, we pick it out and then we compute the maximum interval around tau. And so it's just the clouds of points of data, and the red is the average of the
But
points.
you've done it everywhere.
We did it for several size, for several theta. And yeah, and actually variance decrease in theta. That's a fact. That's easy. And that's it. Thank you very much. Thank you, Yvan.
Merci, Louis-Pierre. Any questions?
All right, thank you for your talk. And maybe one of the more naive question would be: there's a whole zoo of those zeta functions, and that would, for example, give would be related to other number fields or a whole zoo of L functions. Is there such numerics in those cases? And if so, do you know, are random matrices the group that you're looking at to make sure your numerics work out? Does it change, or how does the okay, maybe you understand what I'm saying.
So if you look at the connection between zeta, so other L functions, say, and random matrix, there's other numerics for the, the zeros and all that, and those are important. As far as short interval is, not really, and that's something we're trying to do, because as you said, there's a whole zoo of L functions. And the thing is, if you take the StatMech perspective, if you want to understand macroscopic things, you should understand what's happened at the microscopic level. Okay, that's a bit the approach we take. So if you want to understand the Lindelof hypothesis, how large values are created, well, you should at least understand how large values are created typically. And then maybe that you're going to learn something and extrapolate. So yeah, it's in the next grant. Do other L functions and short interval. Yeah. But it's extremely hard.
Absolutely embarrassing question. What's the distribution of the zeros on the critical? Is it uniform?
No. The gap shrinks. So that's a good question.
So the gap shrinks. So it makes sense to take the interval of integration to be 1. I thought it was too small.
No. So the number of zeros grow like t log t. Okay, so in an interval of order 1, you essentially have log t, and so you have more and more zeros as you go. But that's an important point.
Yeah. May I ask the
yes,
the embarrassing question, which is the elephant in the room? It's the same question I've asked Dyson, so don't worry about it. He didn't give a good answer. What on earth does the similarity between the distribution of the zeros of the zeta function or the minimal energies and the distribution of zeros of eigenvalues of random matrices, what on earth does that have to do with the Riemann hypothesis?
That's a food for thought before lunch.
May I put it?
I would argue none, but
I'd like to put it more sharply, because there are obviously a lot of people who think that the coincidence is not just a coincidence, but that there really is some operator or some element of a universality class of operators whose spectrum somehow coincides with the zeros. But that's not the statement. The statement is that you have a universality class of, or at least to some approximation, of distribution, which is already on the critical line or wherever you want to assign it in the complex plane. And these two completely different things belong to the same universe, or somehow belong to the same universality class. That doesn't mean that you can pick a specific operator within the random class whose spectrum coincides with zeta, because it's that which would be, and an involution, invariance under some sort of anti-linear involution, which makes it stick to the critical line. That would be the Riemann hypothesis, but that's far away from the statistical statement that they somehow, their spectrum or their spectrum belongs to the same universality class.
I agree with you that saying that the zeros of zeta and the statistics of the zeros and statistics of eigenvalues random matrices are in the same universality class. That's that we know that's true essentially, numerically at least. But it's a very different question than saying that you can find an operator whose eigenvalues are the zeros. So I mean it's a tough question to answer, but yeah, I don't think there's. I don't know how deep this connection is. I mean, certainly deep, but it could, again, there's a lot in probability and mathematical physics. There's a lot of objects in the same universality class, but you cannot actually draw a correspondence between them, when you look at it, at finite, before taking a limit or something. So yeah, I mean, I share the same point of view as you.
I don't mean to be immodest, but I think this will be the most embarrassing question, which is
We'll vote on it.
So there'll be a vote afterwards, absolutely. So you were saying that when you've made presentations about this, people have laughed a little bit because you have that log T factor. But it reminds me a little bit of work that was done by Otzelko many years ago, where he was looking at the zeros of the Riemann hypothesis way out there, right?
Yeah.
Is it possible to do something similar here? Do you know what I'm saying?
So way out there though is 10 to the 25, or
Right.
10 to the 30. So log T again.
Still,
it's even if you go up there, you won't see a big difference between log T, log T, and order 1. However, so just to give you an idea, the graph we do. I mean, it's easy to pick up the noise, the signal from the noise. So this is at 10 to the 9. So, you don't gain much in actually going very far for these questions, and even for the zeros. If there's something, you'll see it, very quickly. You don't have to heat the universe like Yvan says to actually see the signal. But yeah. 10 to the 9 is totally fine for this. Even 10 to the 7 is fine. There's not a big difference between 10 to the 7.
The behavior, is there a database of
this database is here.
Did he give the values of the zeros and the maximum?
So this is actually, there's a database online. You can download the zeros.
At least goes work.
It's probably part of at least goes work, but I don't know what the database go up to. So there's kind of I saw a talk actually 2 years ago about this. It's like every zero is unknown up to 10 to the 10 to the 14, and then there's a big gap, and then they know from 10 to the 30 to 10 to the 35. But you're talking about really big numbers, right?
Thank you very much, Louis-Pierre.